Hello, statistics students. The first recording I tried to do did not work. So here is a new one. What we're going to do is play around with the central limit theorem. Oops, shit, I forgot to start. Where did I start? Stop. Oh yeah, there I was. One of those days, huh? So, there we go. There we go. Okay. Central limit theorem, Lab 6. So a reminder of what the central limit theorem means. It says a distribution of means will be relatively normal. Now, there's a couple of conditions on that part. If the population we're sampling from is normal, then the sample size doesn't really matter. If the population we're sampling from is not normal, then we want the sample size to be 30 or more. Under those conditions, we'll find that the mean of our sample means, that's what this says, will be approximately equal to the mean of the population. Now, we usually don't know the mean of the population. The point is to use the mean of the sample means to estimate the mean of the population. It also says the standard deviation of the means is approximately equal to the population standard deviation divided by the square root of n. And so we're going to explore those ideas in this lab. We're going to do it by working with a six-sided die. And a six-sided die, if you remember, is usually considered to be fair, unless it's one of my sneaky ones. Probability of getting a 1 is 1/6. Probability of getting a 5 is 1/6. That's a uniform distribution. Since we're sampling from a uniform distribution, then we're going to want our sample size to be 30 or more. Here I picked a sample size of 40. Instead of rolling a die 40 times or more, we're going to use the rand between function in Excel to generate random die numbers. So let's do that. So in Excel, blank workbook, in cell A1, you want to type equals rand between. And we want numbers between 1 and 6, and it's always inclusive, which means I could get 1 or I could get 6. I got 2. We then want to roll this random dice 40 times. So I'm going to take this, I'm going to fill it down to row 40. So now I have 40 die rolls. What I want next is to know what is the average value of those 40 die rolls, because the central limit talks about the mean of a sample. And so here's a single sample of 40 numbers. Quick way to do that is from the Home tab. To the right, the arrow by AutoSum allows me to grab the average. Excel says, do you want the average of the numbers above? I hit enter for yes, or if it didn't highlight the numbers I want, I re-highlight them with my mouse. Make sure it's closed with a parenthesis and then hit enter. So I found my average value to be 3.27. One downside of the random number generator here is every time I do something, it regenerates the numbers. And so we'll get around that in a minute. Okay, so here I have one mean from one sample of 40. What I want you to do next, if you look at the description, is do 25 samples of 40. So we're going to take these 41 cells and we're going to fill them right through 25 columns. Since there are 26 letters in the alphabet, that means we want to take this over to column Y. All right. So bottom corner on the right of what I've selected, I get the single black plus, I click and drag. That will fill all of those formulas over to column Y. So now I have 25 columns with 40 random dice rolls. At the bottom of each of those, I have these means. Now I really don't care about the dice rolls anymore because the central limit theorem only cares about the means. So I'm just going to make these guys special by making them bold and green or purple. You pick a color you like, highlight them in yellow perhaps. Okay, so these are my special numbers. This is best done in a group because really we would like as many means as possible. I only have 25 right now. So ultimately we want to have at least 100, and I'll show you how to generate those if you're not working with somebody else right now. Before I do that, I just want to find the mean of these means. And so to do that, I use the formula called average, right? And I want to do the average of these new numbers. And they're going to keep shifting for a while. We'll put a stop to that in a little bit. So the mean of my means is 3.4. Yours will be slightly different. I also want to find the STD of these means. And so that's the formula STD, oh gosh, sample, highlight all your means, all 25 of them. And so I'm getting a standard deviation of about 0.28 for my means. Okay, so again, these numbers more accurately are called the mean of the means. And this right here would be the standard deviation, STD, of means. And they're shifting, that's okay. Another way you can force them to shift, and we'll do this later, is if you hit the F9 key, any cell based on a random number generator will regenerate. Okay? The averages are regenerating because they're based on these newly regenerated random numbers. All of my random numbers are between 1 and 6, and they're whole numbers. All right, let's make a histogram. So if I look at this list right here, the smaller numbers tend to be in the low 3s, and I don't know if I see anything above 4, but it's certainly possible. 4.2, okay. So the numbers seem to range between 3 and 4 point something. So as far as my bins are concerned, I'm going to start my bins at 3 and then maybe scale by 1. So I do a 3.1. And usually we want to make more than one histogram anyway. I'll try this one first, and let's go up to, say, 4.2. That might be high enough. Maybe 4.3 to be safe. For the frequencies, and we're going to make a bunch of histograms for this one. We're going to end up with at least 4 histograms, probably more. Always highlight one more cell for frequency. Highlight the data, which is only the means. I only care about the means now. Comma, the bins, close parentheses, then Control-Shift-Enter. There they are. And so I want to graph these guys. And let's include that last row. Hertz. Inserts, recommended charts, bar, okay. So what I have here is a distribution of sample means. The bottom numbers here are my possible sample means. The side numbers are the frequencies. And can you visualize that being kind of bell-shaped, maybe sort of, kind of? Sometimes we need to tweak it a little bit. So I could tweak this a little bit by saying, you know, let's start at, I don't know, 2.95 and scale by 1.1. So I could take the number above, add 1.1, oops, 0.11 to that, and then I could regenerate, oops, by filling this down, so I could play around with other possible histograms. Maybe the scale could be different, scale by 0.12. Somebody earlier in class tried that and they liked their histogram. So you can play around making different distributions by tweaking this one, or you could just make a whole new, make a whole new set of bins and frequencies off to the side. Which I recommend doing. All right, next. We want to scale this up. So let's take a look at the lab. Where are we at? So we have done the initial setup here. We have 25 sample means. We found the average of our means. We found the standard deviation of our means. I've made a couple of histograms, although the earlier ones disappeared just for brevity of this video. Next, I want to get means from at least 3 other people. So I emailed out some means. If you check your email, you would find them. Let's suppose that you did. So let me just bring up my email. Check your email. You wanted to use my means. In your email program, wrong password. They may copy and paste just fine, but they may not. So let's see. Alicia sent some out. I sent some out. Where the heck did mine go? Maybe I didn't send them to myself. Nope. There they are. Okay. So if you got this email, you could copy these guys. And sometimes when you try to paste them in Excel, they paste fine. Sometimes they don't. So, oops, wrong one. I think this is the one we're just working on. Yeah, okay. So I am going to start a new file just to demonstrate something and blow this up for you. So if I try to paste this in here, it's going to basically stick them all in one cell, which is a problem. I can fix that though by going to data, telling the computer to change all that text into columns. It's delimited by a bunch of spaces. So spaces won't be checked for you. Once you check spaces, it'll say, oh yeah, you want me to break these numbers up like that? And I say, yes, please do that. And so now you should see that I do have 25 different sample means from another version of this. So if they didn't paste well, then you'll have to do the data text to columns option to use the spaces to break them into different cells. So I'm going to save this file. So I currently have a couple of files. Let's go back to the other one. Okay, so here's the one I started with you all. I'm going to save this one first. I'm going to have two different files I'm going to work with. You may or may not do the same. Save, browse, Math 243, labs. Let's make a new folder just for lab 6. And I'm going to call this lab 6 part 1. It's my first group of data, and it keeps reshuffling. The interesting thing is my histogram will change. I could use F9 to reshuffle the data, which will change the histogram each time. Save that new file that I imported. So this is the one where I imported the data I emailed out, one set of 25 means. So file, save, browse, find a nice folder. Oops, that's not where I want to be. Oh, there it is, labs, lab 6. And maybe I'll call this one lab 6 part 2. So one way to get extra data is to have other people send it to you. And some people sent theirs out earlier. You may get that. Other way to do it is the following way. We take our selection of randomly generated data here. If we hit F9, it reshuffles it. We highlight those renewed means, and we copy them. In another sheet or another workbook, we can't paste directly because that will give us an error message. Okay, it says reference problem, so I'm going to undo that. What instead I want to do is from the Home tab, I want to hit the arrow under Paste. I want to do a special paste called Values Only. And then it just pastes those numbers in. So then I can go back to that other sheet. I can reshuffle with F9, recopy them, and then here, new line, paste, values only. And I can do that one more time. So 3 extra times, and I'll have 4 sets of 25 or 100 sample means. And we need a little more information to make this look good. So let's see. One more time, F9, recopy, back to my spreadsheet, home, paste special, values only. Okay. Sometimes they'll match, but mostly they're different numbers. So now I want to focus on these means, and I want to repeat what I did before. I want to calculate the average of all of these numbers. So I highlight all of them, all 100. You can do more. Somebody did 125 earlier, someone did 150. One person got crazy and did 1,000. That's fine. All right. So this right here is what we call the mean of the sample means. I'm calling it the mean of means. We also want to find the standard deviation. Equals STD. These are still samples. Highlight all of your data. Again, I have 4 groups of 25. I have 100 of them. This is the STD of the means. Okay. Wouldn't be bad to come up with some bins. I'll just pretty much do what I did before. Frequency for bins. Maybe I'll start at 2.9 this time. And I'll jump up by taking my 2.9 and adding 0.11 or 12, whatever you like. Fill that down a ways. Be sure you're beyond the highest number on your list or close to it. Highlight frequency, one extra cell. Type your frequency command. Highlight your data. And you want to do this a couple of different times. Comma your bins. And so your first histogram is rarely the best one. Usually you have to make more than one. And then don't forget Control-Shift-Enter. Fill it in. And let's look at that graph. Let's see. Insert. Recommended charts. There we go. And again, this is a distribution of sample means. And the central limit theorem says that the distribution of sample means should look relatively normal. Sure, why not? That's almost bell-shaped. I could tweak this distribution by changing my starting point and what I'm jumping by. So maybe I could start at 2.85, a little sooner. And maybe instead of jumping by 0.11, I could jump by 0.12. Maybe that looks a little more normal to you. I kind of like that one. All right, so there's mine. You can make another one. Again, I'm trying to keep this video short. So let's see, what else do I want to do? Next, I need to look at the theoretical distribution. And so I already have that typed up somewhere, but I got rid of it. Okay, we'll just start over. I'm going to add a new sheet here. And this one is going to be the theoretical distribution. Blow it up. All right. So x is a possible number on a dice. 1, 2, 3, 4, 5, or 6. Probability, theoretically, of any one of those. Sorry about that. Is always equal to 1/6. It's about 0.16, 17. Fill that down. To get the mean of a distribution like this, I have to use the sum product command. Highlight my x column, comma, and the probability column. So the mean here is exactly 3.5. So the central limit theorem says the mean of the mean should be pretty close to 3.5, the population mean. Now usually we don't know the population mean, and we're using this to predict it. In my previous example, I had a mean of 3.57. I did it a bunch of times earlier. Pull these guys up. I have a mean of 3.57 there. A mean of 3.56 here. And this one is a mean of 3.43. Okay. So the mean should be near. The more of these samples that I do, or if I make my sample size of 40 bigger, those two different variables will get me closer to the population mean. So I could do more samples of 40 or do samples of a size bigger than 40 at a time. Those are my options to get a better estimate. All right, back here to theoretical. Standard deviation is a bit more of a pain in the butt. That's where we have to use the square root of the sum product. So SQRT of the sum product. And then I have to find the deviation. So I add another parenthesis. Deviations, take your x column data, subtract your mean, and then square that. So those are my deviations squared, comma, my probabilities. We did that a couple of times in class. Kind of a crazy formula. You might want to pause this to try it. And it says I have a mistake and it wants to correct it. Oh, I forgot to type the last parenthesis. Yes, that's correct. Thank you very much. And you should get about 1.7078. So again, that formula, finding the standard deviation of a probability distribution or relative frequency table looks like that. Okay, so what does the central limit theorem say? The central limit theorem says that the standard deviation of the sample's means will not be the same as the population mean. You have to adjust with the square root of your sample size. So I'm hoping to get about 1.7. If I look back here, I get about 0.28. However, I can fix that by multiplying it by the square root of 40. So if I take my sample standard deviation, multiply that by the square root, SQRT, of 40, and I can estimate 1.7-ish, the population standard deviation. Central limit theorem actually states it backwards. The central limit theorem says if you take, where the hell did you go? Down here, theoretical. If you take the population deviation and you divide it by the square root of 40, that's about what the standard deviations of the sample mean should look like. So about 2.7-ish. And if we look at my other problems, my other trials, about 2.7. About 2.7. I show more decimal places, you can see it's not quite 2.7, 2.695-ish. 2.4, that was a little low. Every sample is unique, just like every person. So there's going to be variation, there's no doubt about that. So we're pretty much done with all the calculations we need to do. The last step is for you to just try and answer the discussion questions. So I'll go a little bit of that. Okay, so we did all this theoretical stuff. I didn't make a histogram for the distribution, but that's easily done here. I just highlight the table and go to Insert, Sheets. I get this very uniform distribution. So this is a uniform probability distribution. Not at all bell-shaped, right? And so again, the central limit theorem says that regardless of the distribution of the population, if your sample size is 30 or bigger, and you do a bunch of those samples, the distribution of means, which is what this is, should be relatively normal. So if we did check what's within one standard deviation, what's within two standard deviations of this, we should find pretty close to 68, 95, and 99% for within 1, 2, and 3 standard deviations. So that's something extra you could do if you want. I didn't ask for it. Oops, wrong button. Discussion questions. Describe the shape of the distributions for your sample means, both the one you did for 25 and the one you did for 100 plus. Okay. Are they bell-shaped? Are they not? Compare the mean of the sample means to the theoretical mean. The theoretical mean is 3.5, where your sample means was the mean of your sample means close to 3.5. Compare the standard deviation to the population standard deviation. So that's where we have to use this formula here. And this says, again, the standard deviation from the sample means should be a little smaller than the standard deviation of the population, because basically when we compress a bunch of information down to an average, we used to have 40 pieces of information. The average means we're condensing that down to 1. And when you condense that information, you shrink your knowledge. So we have to shrink the standard deviation to compensate, is pretty much what that says right there. Was that close? Population says I should be getting about 1.7 divided by the square root of 40. That calculation came out to be 2.7-ish. And so I should see that my sample mean standard deviations were about 2.7-ish. Eventually I hit the right button. There we go. Again, using the examples in this experiment, state in your own words what the central limit theorem means. In those statements, you should be discussing the shape of the distributions you found, the relation between means of the samples and means of the population, and standard deviations of both the means and the population. All right, that's it. Hope this helps. Should be a little easier than previous labs. Go forth, do good math, take care, have good weekends. I can figure out how to shut this off.